Hi, welcome to 18.7. We will focus our attention today on acid-base properties of salt solutions. So really the question that we're answering in this entire section is whether a salt dissolved in water is going to be acidic, basic, or neutral. And that all stems from where the cation and the anion originate. So what is their conjugate, acid or base, that they are dissociating from? Okay, so let's first look at table 3. So table 3 looks at solution of conjugate acids and bases. So original acid or base, let's say we started with a strong acid. It dissociates and forms an anion that is neutral. What do I mean by that? So let's give an example. Let's say our strong acid is HCl. When it dissolves in water, the anion that dissociates is Cl-. Now, Cl- chloride isn't neutral in the sense that its charge is neutral. It's neutral in the sense that it does not react with water. Therefore, it does not change the pH. So that's what we mean by neutral. Neutral, we mean, does not affect pH. Great. So let's look at another example, a strong base. So if I take the strong base sodium hydroxide and I dissolve that in water, I'm going to form a neutral cation, namely sodium ion. That sodium, although positively charged, also does not react with water, and therefore it is also neutral. So anytime you have a strong acid or strong base and they dissociate in water, their dissociated ion is going to not affect the pH of the solution. However, if you have a weak acid or a weak base, let's give an example, maybe acetic acid. Now, when that dissociates, the anion that forms is acetate. And a weak base, let's say ammonia. When it dissolves in water, the cation is going to be ammonium. Both of these actually do affect the pH of the solution because they react with water. This right here, the acetate, reacts with water to form a basic solution, and ammonium reacts with water to form an acidic solution. Now, just to kind of drive this point home, let me show you how that's true. So let's take the example of the, where's my highlighter? Of the chloride, and then we'll take the example of ammonium. So why doesn't chloride affect the pH of the solution? So think of Cl-. If you put it into water, in order for it to react with it, the only thing that it could theoretically do, because it's negatively charged, is strip a proton from water, and you would create hydrochloric acid and hydroxide. That needs to look really weird to you because hydrochloric acid is a strong acid. It will never reform in water because it is a strong acid. Notice also you're forming hydroxide. These would immediately react to form these products again. So that means this reaction will not occur. That doesn't occur. So that's why chloride forms a neutral solution. And excuse the crying in the background. Okay, let's look at ammonium as another example. Ammonium plus water. Now, what could this do? Could ammonium do in water? Well, it has a positive charge. That means it likely has a more acidic hydrogen that is associated with it. Ammonium could protonate water to form hydronium and ammonia. Ammonia is a weak base, therefore it will reform. Hydronium is created, which means that ammonium is creating an acidic solution, which is what we just stated over here. Okay, so that was a lot of the reasoning that we're going to use to determine the pH or the relative acidity or basicity of salt solutions going forward. So as a reminder, a salt solution or salt itself is just a metal and nonmetal, or generally speaking, a cation and anion. Now we're going to apply that to this next table. So we know that a salt is going to contain both components, a metal and nonmetal, or a cation and an anion, to form a neutral compound. And when I say neutral in this sense, I mean there is no resulting charge between the two. The two ions balance the charge out to have a neutral compound. Okay, so this is the way that we're going to read this table. We're going to read it left to right. Left to right, not up to down, but left to right. Okay, so let's start off in this first row. So let's say you have an anion that is weakly basic. That's what WB means. And you have a cation that's neutral. Together they would form a basic solution. So we're not in this case looking at where the anion came from or where the cation came from. We're just saying that, let's say in this instance, a neutral cation would be something like sodium. Okay, it's neutral, it doesn't react with water. And in this case, if you have a weak base anion, that would be something like acetate. Okay, so if you have an anion that's weakly basic and a cation that's neutral, all together the solution will be basic. If you have an anion that's neutral and a cation that's acidic, the solution will be acidic. If you have an anion that's neutral and a cation that's neutral, the solution will also be neutral. And let's say you have an anion that's basic and a cation that is acidic. In order to know the solution type, you have to compare which one's stronger. Do you have a stronger acid or do you have a stronger base? So there's a lot of information here. Let's use some examples to kind of work through this, and also working through our salt solution flow chart right here. So the salt solution flow chart breaks down your salt into a cation and an anion, and then it has you ask or answer certain questions. So our salt can be broken down into a cation and an anion. You must ask yourself, let me kind of move this over so I have space. You must ask yourself first, does the cation originate from a strong base or weak base? Okay, that's really the only question you're asking. So let's say the cation is sodium plus. So what type of base is the only option, what type of base did sodium originate from? Well, the only option for sodium to come from a base is if sodium came from sodium hydroxide and it went into water and it dissociated into sodium ion and hydroxide, right? It's the only place that sodium could come from. Okay, so is sodium hydroxide then a strong or weak base? It's a strong base. Therefore, sodium itself is neutral. So the cation is neutral. Sodium plus is neutral. Let's do the same thing with an anion. Let's say our anion is C2H3O2 minus. Okay, so acetate is our anion, which means our salt was sodium acetate. Okay, so that's the salt we are evaluating to see whether it is acidic or basic or neutral. And we split it apart into our cation and anion. Our anion then is acetate. Where did acetate come from? Did it come from a strong acid or a weak acid? Well, its original acid before dissociation, before losing an acidic proton, is acetic acid. And because acetic acid is weak, it produces a slightly basic anion when it dissociates. So yes, it dissociates into acetate and H+, but of course we're focusing on the acetate. So we ask a very similar question like we did with the cation. Does the anion originate from a strong acid or weak acid? And the answer is acetic acid is weak, therefore the anion is weakly basic. So acetate is weakly basic. Now if we go back up to the top, this table right here, we can identify what type of solution we'll have based on the cation and anion. So let's start with the cation. So we have a neutral cation. So let's see, neutral cation right there, neutral cation. And then we have a weak base anion, weak base anion, weak base anion. So it looks like the only time that those two overlap, where we have a weak base anion and a neutral cation, that makes a basic solution. So the answer then is that we create a basic solution. Okay, so you're looking for the row that has both the cation and anion that you just identified. So neutral and weak base is right here, therefore solution type is basic. All right, so let's do some practice. Okay, here, example question 1, determine whether the following salt solutions are acidic, basic, or neutral. So I'd like you to pause and try A and B on your own, and then come back in a minute to see the answer, and then we will do C together. C is a lot more complicated. So pause the video now. Okay, for sodium chloride, that breaks apart into sodium and chloride individually. So let's start with our cation using the flow chart that was on the previous page. We asked the question, does sodium originate from a strong base or a weak base? Well, sodium comes from sodium hydroxide, which is a strong base. Therefore, sodium is neutral. All right. Chloride, does chloride come from a strong acid or a weak acid? It originates from hydrochloric acid, which is a strong acid, therefore chloride is neutral. Since both ions yield neutral solutions, the entire salt solution is also neutral. Great. Okay, potassium acetate, we split apart into potassium ion and acetate anion. And we asked the question, does potassium originate from a strong base or weak base? Well, its conjugate base is potassium hydroxide, and that is a strong base. Therefore, potassium yields a neutral solution based on the flow chart. Okay, let's look at acetate. Acetate comes from acetic acid, which is a weak acid. Therefore, acetate yields a weak base solution. So if you look at that table on the previous page, you'll notice that a neutral cation, and a weak base anion yield a basic solution. So your answer here should have been basic, yields a basic solution. Okay, let's move on to part C. Okay, lithium hydrogen phosphate. We want to know whether it yields an acidic, basic, or neutral solution. So we're going to start off with the same method. Let's look at lithium. Okay, so lithium, does it come from a strong base or a weak base? Lithium comes from lithium hydroxide, which is a strong base. Therefore, lithium itself is neutral. Okay. So lithium does not affect the pH of the solution. What about hydrogen phosphate? Okay, this one I cannot actually use the flow chart because hydrogen phosphate is amphiprotic, which means it can act as an acid or a base. So example, as an acid, it can react with water. to form, of course, hydronium and the conjugate base, which is phosphate. It can act as a base, so the same species, hydrogen phosphate, can act as a base to strip a hydrogen from water and create hydroxide and dihydrogen phosphate. Okay, so those are the two examples. So what I need to do is I need to find the Ka of hydrogen phosphate, and I need to compare it to the Kb of hydrogen phosphate. So that is an odd little, I have no idea what that is. Okay, there. And I need to see which one is stronger. So let's try this again. I need Ka versus Kb. If Ka is greater than Kb, then the species is acidic. And then where do I put this? I'll put it here. If Kb is greater than Ka, it is basic. So that's the simplified version. I need the Ka and the Kb for hydrogen phosphate. Okay, so notice what is given to me. I'm going to erase this little portion right here just so I have some more room. So what's given to me up here is all the Ka values of phosphoric acid. And the reason that those are given to me is because that gives me information about hydrogen phosphate. So let's think for a second about phosphoric acid. So phosphoric acid has 3 acidic hydrogens, H3PO4, which means it has 3 Ka values. Okay, so when hydrogen phosphate first reacts with water, that is referred to as Ka1. After it loses a proton and it reacts with water again, that is called Ka2. And the last hydrogen to react with water, that is referred to as Ka3. Ka1, Ka2, Ka3. Now I'm not writing the balanced reaction because it's not particularly important in this scenario, but that is what those Ka values refer to. Okay, so which of these Ka values gives me the Ka for hydrogen phosphate right here? Well, obviously it's this one. It's the last one that I wrote, Ka3. So the first Ka refers to the losing of the first hydrogen. So this has all the hydrogens. It's about to donate one to water. So that's the process of it losing the first one. Ka2 is losing the second one, and Ka3 is losing the third or the last hydrogen. So I have my Ka value for hydrogen phosphate. Ka3 is the Ka for hydrogen phosphate, which is equal to what we have up here, 4.5, let's erase that, 4.5 times 10 to the negative 13. Great. But I still need Kb. All right, so let's zoom this out. Okay, give myself a little bit more room too. So relationship between acid and base dissociation. So notice right here that Ka times Kb equals Kw. This gives you really important information for this problem. So this means the acid Ka times the Kb of the conjugate base is equal to Kw, which is 1.00 times 10 to the negative 14. That is a constant. All right. So that means in order to find Kb, I have to take the Ka of the conjugate species, the conjugate acid, to get Kw. Okay, so let's, or sorry, not to get Kw, to get Kb. So let's write that out. So Ka times Kb equals Kw. Okay, but which Ka do we use? So this Kb is referring to hydrogen phosphate. Okay, that's the species that I'm trying to solve for, right? Hydrogen phosphate. So the question is, what is the conjugate acid? The conjugate acid of hydrogen phosphate is dihydrogen phosphate, right? With an additional hydrogen. Okay, so what Ka value is that? So I know I want the Ka of hydrogen phosphate. Well, let's look back over here. Let's look for dihydrogen phosphate. That corresponds with Ka2. So that's the second hydrogen that's going to be deprotonated. So Ka2. Ka2 is given up ahead, or up at the top. So the Ka, where do I write this? What's the best place? Let's give myself some room. So that's going to be equal to 6.3 times 10 to the negative 8. All right, so let's plug that in. So Ka, which is 6.3 times 10 to the negative 8, times Kb, which I don't know, right, is equal to 1.00 times 10 to the negative 14. So that means 1.00 times 10 to the negative 14 divided by 6.3 times 10 to the negative 8 is going to be my Kb. Okay, I'm plugging that into my calculator. All right, that gives me 1 point, and do we round? Yeah, let's round now. 1.6 times 10 to the negative 7. All right, so I'm going to highlight in yellow the most important numbers. So that's my Kb. And then the Ka that I'm going to compare that to is right here. All right, so what we want to decide is whether Ka or Kb is greater. So it looks like Kb is greater. So we said below here, if Kb is greater, than Ka, we have a basic solution. So that is your final answer, or we have a basic species. So that is your final answer also, because the lithium doesn't have any impact on the pH of the solution. It's totally neutral, but hydrogen phosphate is mostly basic since the Kb is greater than the Ka. Therefore, you have a basic solution. So what people often ask is, okay, why again are we using this Ka? Because what we want is the Ka versus the Kb for hydrogen phosphate. So I need the Ka for hydrogen phosphate, which is Ka3 right here. Ka3 is given to me up here, which is 4.5 times 10 to the negative 13. All right, so that is the most complicated type of problem that you are going to see on the exam. All right, last we're going to look at Lewis acids and bases. So remember, at the very top of the notes for chapter 18, a Lewis acid is an electron recipient, and a Lewis base is an electron donor. Okay, so that's what we're using to identify A and B in example question 1. So I want to label the reactants as Lewis acid or Lewis base. I think the best way to do this is looking at the Lewis structures, because it really shows you where the electrons are going. So for A, I have calcium ion next to oxygen ion or oxide, and that is reacting with carbon dioxide. Okay, so your final species, calcium carbonate. You're looking to see where the new bond was formed. So originally carbon just had a bond, a bond to 2 oxygens. Now it has a bond to 3 oxygens. Well, where'd that oxygen come from? Right here. So that means that these electrons went to this carbon. So looking back at what an electron recipient and electron donor are, that means that this carbon dioxide received the electrons, so this is my Lewis base. And the oxygen donated the I totally did that opposite. Glad I realized that before I posted this. Okay, this is my Lewis acid. It's an electron recipient. And then the oxygen donated the electrons, so that's my Lewis base. All right? So pause the video, try B right now, and then come back to see the answer. All right, welcome back. These are the Lewis structures for B. So let's look at where that new bond was formed. So there is a new bond between boron and nitrogen, which means these little lone pairs went and formed a bond with boron, which makes the Lewis acid boron trifluoride and makes the Lewis base ammonia. All right, let me know if you have any questions, and that wraps up for us chapter 18.